Hello, in this video I'm going to talk about the cosmological principle, which is one of the more philosophical parts of physics because it's dealing with the preconditions and the assumptions that are required in order to conduct cosmology at all. Now, we have a problem with cosmology, which is the description of the universe and how it evolves, because the universe is enormous and we've only got access to a small bit of it. So it raises the question of what can we confidently say about the behavior of things in other parts of the universe. Is what we do on Earth representative of what's going on in other parts of the universe that we don't have as much access to, or in some cases don't have any access to at all? Now, before I go into the details of the cosmological principle, we have seen something like this before. If you go all the way back to the start of these videos before I went into classical mechanics, I set up a framework of assumptions there, one about space, that space is flat, that we could use Euclidean geometry, the other one about time, that time was universal throughout space. Now, I said at the time with that we know that those aren't our most accurate descriptions. More accurate descriptions are given by general relativity, but they were good enough assumptions in order to allow us to start classical mechanics and then make some scientific progress. Now, this is slightly different with the cosmological principle because we're not saying that the assumptions in the cosmological principle are approximations. We're saying that these are actually things that we think are true. So there's a slight difference there to what I was doing with classical mechanics. But there is a similarity that we're saying, well, without this framework, without these assumptions, we can't actually get going and we can't make any scientific progress. So this idea of setting up a framework is not limited just to cosmology. Right, okay, with that in mind, let's get on then to the cosmological principle. What we're really saying with this is the universe looks the same wherever you are, that we're in a representative bit of the universe, and if we're in a representative bit, a fair sample, then it's fair enough to say, well, whatever goes on here goes on everywhere else. Whatever laws of physics and whatever discoveries we make on Earth, we can then say are applicable to other parts of the universe. So this depends on this idea that we are seeing a fair sample. We are in a representative bit of the universe. So based on that idea, we're saying, okay, well, the laws of physics apply everywhere, all space and time. Laws of physics apply to all space and time. All space and time. Because if we're in a representative bit of the universe, then why would these laws be different somewhere else? We're saying that the universe is homogeneous, as in we've got an even distribution of matter across the universe at a large scale. So this is our distribution of matter. And okay, at a small scale, we know that isn't true. Matter clumps. A star or a planet is a clump of matter. A galaxy is a clump of clumps of matter, etc., etc. But you go to larger and larger scale, everything looks more and more the same. So this is something which is supported by our observations, and it supports the idea that we are in a representative part of the universe. This is already touching on the idea that the universe is isotropic. And isotropic because everything looks much the same in all directions. There's no center to the universe. There's no edge to the universe. If you had a center or an edge, then things wouldn't look the same in all directions. You'd be nearer the center, you'd be nearer the edge. It might then affect distributions of matter. People find this idea of no center and no edge a little bit weird because they have an idea when they start out of the Big Bang as being some point. So this is where the universe started, which they see as being the center, and then it expands outwards. And well, if it's expanding outwards, well, that must be the edge then, the edge of the expansion. Now, okay, the actual maths describing all of this, the maths and the physics is quite complicated, but to just give a simple example, okay, this isn't exactly how the universe is, but it will shed some light on this idea of no center and no edge. Say we were just thinking about some point and you've got a sphere that's getting bigger and bigger. So this sphere just keeps on growing. Well, say all you knew about was the surface of the sphere. So you only knew about the 2D surface of that sphere. Well, the surface of the sphere doesn't have a center and it doesn't have an edge. It keeps on expanding. So the actual surface area keeps on getting bigger and bigger, like the space is expanding in the universe, but it still doesn't have a center or an edge. If you were an ant crawling around the surface of that sphere, well, you wouldn't get very far if you were a member of the Ants Flat Earth Society and you're wandering around looking for the edge to drop off of, because there isn't one. You just keep going round and round and round. So you get those sort of descriptions of how the universe is actually, in reality, formed and how it exists. So these are the ideas that feed into the cosmological principle. They get expressed in different ways, but they all come back to this idea that we are in a representative sample of the universe, which means what we do here and what we discover here, we can then apply everywhere else. And you can see why this is important, even if you go back to Newtonian times and we are dealing with classical mechanics. So, I mean, how would Newton construct his universal law of gravitation without the assumption that what he was discovering and doing on Earth was applicable somewhere else? I mean, he had to say it was applicable throughout the solar system at least. Otherwise, how is he going to describe how these planets are going around the sun and such like? I mean, you can't do it without making that first step into cosmological principles. And then, of course, this then feeds into all of our cosmology of how we're then describing the universe, how we're building our cosmological models. Because if we're observing things in the universe and we're doing, looking at distant galaxies and quasars and all these other objects, we're saying, okay, we're looking back in time. The further we are looking away, we're looking back in time because of the time it takes for the light to get us. So we are looking through space and time. We're seeing things that are different. So say you look a long way back in time, you look at very, very distant galaxies and you're looking at these very distant quasars and such like, and you look at the difference in concentrations between different elements. So you look further back in time and there are fewer of the heavier elements compared to what we see locally. So we've got a difference here. We've got a difference between what we're seeing locally and what we're seeing far away. The question is then, what is it that is causing the difference? Is it because we're looking back in time, so there's a difference in time, or is it because we're looking a long way away, in which case it's a difference in location? Now, if it's just a straight difference in location, that we've got lots of heavy elements over here and there aren't over there, then we're going against the cosmological principle here because we're not getting this homogeneous distribution of matter. So that's causing us a problem. We can say, oh, there's a difference in time. So if we're saying, well, actually, this is time 1 over here, this is time 2 over there, or this would be in the past, time 2. So we're looking back in time. But we can then build a model of the universe that will then describe why things were different back in time. As in, you have to go through stellar life cycles, say, in order to create these heavier elements. You have to go through these processes of, a star going to supernova and things to actually create these heavy elements. So the cosmological principle is then driving the way we then describe the universe, because we're saying we're in a representative part of the universe. So you can see why this is so important, but it is a set of assumptions. We've got no way of saying, completely concretely, oh yeah, this is definitely true. We can't go to a distant galaxy in the past and say, oh yeah, let's run our tests and see that we get the same results for all of our theories. We have to work these things out. And that means coming up with theories which are applicable in the past. We see this in these cosmological models. People talk about the early universe and how the fundamental forces were unified. We talk about gravity and electromagnetism and strong force, weak force and such like. We talk about those commonly as separate entities. okay, we have it in our minds that, yeah, okay, there's the electroweak force we start talking about and things like that. But in the early universe, there's talk about, yeah, these were all unified. So we need to then construct laws of physics that are applicable at that level of detail in those conditions. So it puts an onus on us in order to describe things in a certain way, in order to look for certain descriptions. So without the cosmological principle, we're not being guided in that way. Now, this does raise a few concerns, and this is where you get into the philosophical part of all of this. And Karl Popper, the famous philosopher, so yeah, he was talking 1950s, 1960s, this sort of time. He was, well, he lived pretty much for the duration of the 20th century. He had an issue with things like the cosmological principle because he was saying, well, our reason for knowing, in inverted commas, how the universe has evolved and how the universe is structured and behaves. So our cosmological model, if we say this is a cosmological model, our Big Bang theory, this is what we know about the universe. So that's what he means by knowing. So our reason for knowing the Big Bang theory is that we don't know stuff about other parts of the universe. We've made these assumptions. These are assumptions made on a lack of knowledge, and on the back of that lack of knowledge, we then claim knowledge about the universe. So it makes some philosophers of science a little bit uncomfortable, this approach. But there are, there is evidence that we can gather to support these assumptions. It's not like they're completely nuts, that we're doing this completely in the dark. We can observe a lot of the universe. We can see the distribution of matter. We can look at things like the cosmic microwave background and say, oh yeah, well, this within acceptable statistical variations, this is isotropic. So we can look at a lot of these things. We can get strong implications that things were causally connected in the past. We've got that evidence that the Big Bang is a good model. Some of it is circumstantial evidence. There's only so far we can push these things because we've only got limited access to the universe. But if you've got a lot of things pointing in one direction, then we can make scientific progress by setting up a framework of assumptions, making some progress, and then when we encounter things that go against those assumptions, then revise the assumptions. So it's a pragmatic way of going about science. And okay, Karl Popper, he had a bit of an issue with this, but he famously had a spat with people. You had Thomas Kuhn was another one who, yeah, he was operating at a similar time to Popper. They were contemporaries. And he was saying, well, this is how science is conducted. This is what you do. You can't question every single assumption every time you do an experiment. He was saying you've got these periods of what he called normal science, where normal science is saying, okay, well, I'm not going to question the framework, or as he put it, the paradigm that I'm operating within. I'm going to assume a particular paradigm of assumptions, so like the cosmological principle, conduct a whole load of science, a whole load of normal science within that framework, and then see how I get on. We'll make a whole load of scientific progress. Eventually, you'll get to a point, maybe, where all of the reservations that start coming up, you're going to get more and more conflicting evidence. And all this conflicting evidence is going to keep on building up and building up and building up until eventually you think, right, okay, we've got to change our paradigm. Kuhn was the person who came up with the idea of the paradigm shift. And then, okay, right, we need a new framework now. We need a new paradigm, and then we can go back to conducting normal science again. And we've seen this happen. People operated within the assumptions of natural philosophy, all the stuff that Aristotle came up with. And then we had a scientific revolution, and we ushered in Newtonian classical mechanics and other forms of classical mechanics. That went along fine. People were operated within that, but the objections and the counter evidence just kept on building up and building up until eventually it's like, okay, we need something new here. We need a new description, which is going to take account of all of this. And then you get relativity comes in, paradigm shift again. That doesn't mean to say you throw out everything that happened before. We still use classical mechanics, but there's a new paradigm. if you want to start describing things in more detail, with more accuracy, you need to operate within the paradigm of general relativity. In this case, we've got the paradigm of the cosmological principle. So again, the same sort of thing applies. We conduct science within that paradigm. If the counter evidence keeps on building up, we have to either modify the assumptions or come up with a new principle. But there is quite a lot of supporting evidence, as I've already mentioned, for these assumptions within the cosmological principle. We can't get to the stage of being certain about it all, but it's looking pretty good and it's allowing us to make scientific progress. So make of it what you will. So anyway, there you go. That's a description of what the cosmological principle is, why we need it, and some potential problems